Welcome back to another video. Let's jump right into the topic of basics of probability theory. Uncertainty can be defined as the variation in the outcome given the setup of the experiment. It is an irremovable part of any experiments, and predicting uncertain events can be very valuable. Consider two events, rolling a pair of dice and the sunrise. Predicting that the sun will rise is less valuable than predicting the outcome of rolling dice because of the level of certainty involved. The sun rising is a highly predictable, almost certain event based on astronomical patterns that have been consistent for billions of years. It carries little uncertainty, so its prediction doesn't provide much new or actionable information. On the other hand, predicting the result of rolling dice is valuable precisely because it is uncertain. Rolling dice involves randomness, where multiple outcomes are possible, each with its own probability. Predicting the dice roll result, even if only in terms of likelihood, like knowing each number has a 1 in 6 chance on a fair die, gives insight into how to manage, interpret, or strategize around that uncertainty. In engineering and decision-making contexts, understanding and making predictions under uncertainty, like the dice roll, is valuable because it mirrors real-world situations where outcomes are not guaranteed and risk management is essential. Uncertainty is essential in engineering because it reflects the unpredictability in real-world systems and prepares engineers to handle incomplete or variable information. As engineers, we often make decisions with limited data, and understanding uncertainty helps us create resilient, safe, and effective designs. By recognizing uncertainty, we improve our problem-solving skills, make more informed decisions, and manage risks better. This concept underscores the importance of data collection, testing, and adaptability, as engineering systems must operate reliably even when unexpected events arise. Embracing uncertainty is a powerful tool, allowing engineers to develop solutions that perform well in diverse and challenging environments. An experiment in statistics is a process designed to observe outcomes, and it typically leads to one of several possible results. For instance, rolling a die is an experiment because it yields one result from a set of 6 possible outcomes, 1 through 6. Other examples include tossing a coin, yielding heads or tails, or counting the number of customers entering a bank on a Thursday afternoon, which can vary based on random factors. These experiments are characterized by their unpredictability. While we can define all possible outcomes, we cannot know the result of any single experiment until we actually perform it. A statistical experiment is considered a random experiment because the outcome is influenced by chance, and it cannot be known beforehand. Even if we conduct the experiment under the same conditions multiple times, each trial can produce a different result. For example, each time we roll a die, we might get a different number, or each Thursday, a different number of customers might enter the bank. This variability is at the heart of probability and statistics, as it allows us to model and analyze patterns and likelihoods in the face of uncertainty. To model and analyze a random experiment, statisticians use probability theory. Probability is a numerical measure of how likely it is that a specific event will happen, providing a way to quantify uncertainty. The value of a probability ranges between 0 and 1. If an event has a probability of 0, it is impossible for that event to occur. Conversely, if an event has a probability of 1, it means the event is certain to happen. A probability of 0.5 indicates that the event has an equal chance of occurring or not occurring, like flipping a fair coin and getting heads. The rule that the sum of probabilities of all possible outcomes adds up to 1 is fundamental in probability theory. This is because probability accounts for every possible outcome within a defined sample space. For instance, in rolling a fair 6-sided die, each outcome, 1 through 6, has a probability of 1/6, and the sum of all these probabilities is 1, representing certainty that one of the numbers will appear. This principle helps ensure that probability values are consistent and meaningful, allowing them to be used in various fields to predict outcomes, assess risks, and make informed decisions. In probability, a sample point is a single possible outcome of an experiment, while the sample space is the set of all possible outcomes for that experiment. The sample space provides a complete view of everything that could occur, which is crucial for calculating probabilities and understanding the behavior of the experiment. For example, in tossing a coin, each sample point is a possible outcome, either head or tail, and the sample space is the set of head and tail. For rolling a six-sided die, the sample space is a set of numbers 1 to 6, since any of these 6 outcomes could occur. In other cases, the sample space may have more outcomes, or even an infinite range. If we draw a card from a deck, there are 52 possible cards, so the sample space consists of all these unique cards. Sample spaces can also represent broader or continuous possibilities. For instance, if we measure the height of the next customer entering a clinic, the outcome could be any real number within a range, for example, between 0 and 10 feet, which represents a continuous sample space. Likewise, the demand for a product in the next year could take on any number greater than 0, whether an integer or a real number, representing a potentially unbounded or continuous sample space. These examples highlight how sample spaces vary based on the nature of the experiment, from finite and discrete sets, like dice rolls, to continuous ranges, like measurements, helping structure how we approach probability and make predictions about possible outcomes. An event in probability is a specific set of outcomes from the sample space that share a characteristic of interest. Events allow us to focus on certain types of outcomes that are meaningful to a particular study or question. For example, consider the experiment of rolling a six-sided die with a sample space 1, 2, 3, 4, 5, 6. If we define the event A as obtaining an odd number, then A consists of the outcomes 1, 3, 5. Similarly, we can define another event B as obtaining an even number, which includes the outcomes 2, 4, 6. Each of these events groups together outcomes that share a common feature, odd or even results, allowing us to calculate the probability of rolling an odd or even number by looking at the outcomes within those events. Events can represent any subset of the sample space, so they're versatile tools for analyzing specific scenarios within the broader set of possible outcomes. Now, let's answer these questions. What is the sample space? What is event A? What is the probability of event A? What is event B? What is the probability of event B? Let's break down each part using the example of rolling a fair six-sided die. The sample space is the set of all possible outcomes when rolling a die. So, for a six-sided die, the sample space is a set containing numbers 1 to 6. Event A is defined as obtaining an odd number. The odd numbers on a six-sided die are 1, 3, and 5. Therefore, event A is a subset containing numbers 1, 3, and 5. Event B is defined as obtaining an even number. The even numbers on a six-sided die are 2, 4, and 6. Thus, event B is a subset containing 2, 4, and 6. Probability of event A happening can be calculated by dividing number of outcomes in A by the total number of outcomes in sample space, which is 3 divided by 6, equaling to a probability of 0.5. Similarly, the probability of event B is the ratio of favorable outcomes, even numbers, to the total number of outcomes. Since there are 3 even numbers out of 6 possible outcomes, which results in 0.5. Thank you for your attention, and see you in the next video.